Hello everyone, I am Sachin and I am from First MSc Chemistry JSS Uti Road. So today I am going to explain about UV visible spectroscopy. So before going to the topic, let us understand what is spectroscopy first. It is a branch of science that deals with the study of interaction of electromagnetic radiation with matter. So what is electromagnetic radiation then? Electromagnetic radiation consists of discrete packages of energy which are called as photons. A photon consists of an oscillating electric and an oscillating magnetic field which are perpendicular to each other. So here on the screen you are seeing that the structure of wave. The structure of wave consists of crusts and trumps, where this A represents the amplitude and the lambda represents the wavelength. The relationship between the wavelength and the frequency can be written as C is equal to V lambda. As photon is subjected to energy, so epsilon is equal to HV is equal to Hc bar lambda. So this is the 3D structure of wave, and it is an electromagnetic radiation. So let us understand what is frequency and what is wavelength. Frequency, it is defined as number of times electric field radiation oscillates in one second, and the unit is hertz. So 1 hertz is equal to 1 cycle per second. So coming to wavelength, that is lambda, it is the distance between two nearest parts of the wave in the same phase, namely distance between two nearest crests or trumps. C is equal to lambda V. As photon is subjected to energy, so epsilon is equal to HV is equal to Hc divided by lambda. So let us understand, let us know what are the principles of spectroscopy. The principle is based on the measurement of spectrum of a sample containing atoms or molecules. The spectrum is a graph of intensity of absorbed or emitted radiation by sample versus frequency or wavelength. Spectrum is an instrument designed to measure the spectrum of a compound. So this is where you can see the wavelength. It is an visible light here, and and it is in purple color. There is a 400 nanometer, and in blue and green near this color it is a 500 nanometer, and in orange that is 600 nanometer, and in red it is 700 nanometer. So and another principle of a spectroscopy is, that is absorption spectroscopy. An analytical technique. This absorption spectroscopy is an analytical technique which concerns with a measurement of absorption of electromagnetic radiation. Example, UV, that is 185 to 400 nanometer, that for visible 400 to 800 nanometer spectroscopy. IR spectroscopy, for IR spectroscopy, that is 0.76 to 15 micrometer. So coming to emission spectroscopy, an analytical technique which means emission of a particle or radiation is dispersed according to some property of the emission, and the amount of dispersion is measured. Example, mass spectroscopy. Interaction of EMR with matter. So electronic energy level at room temperature, the molecule are in the lowest energy levels, that is epsilon naught, where the molecules absorbs UV visible light from EMR. One of the outermost bond or lone pair electron is promoted to higher energy state, such as E1, epsilon 1, epsilon 2 and epsilon naught, so on, epsilon naught, etc. is called as electronic transition, and the difference is as delta epsilon is equal to HV is equal to epsilon naught minus epsilon naught, where n is equal to epsilon n minus epsilon naught, when n is equal to 1, 2, 3, etc. And delta epsilon is equal to 35 to 71 kilocalories per mole. So coming to vibrational energy level, these are less energy level than electronic energy levels. The spacing between energy levels are relatively small, namely 0.01 to 10 kilocalories per mole. Example, when IR radiation is absorbed, molecules are excited from one vibrational level to another, or it vibrates with a higher amplitude. So rotational energy level, these energy levels are quantized and discrete. The spacing between energy levels are even smaller than the vibrational energy levels, where delta E rotational is smaller than delta E epsilon vibrational, which is smaller than delta E electronic energy transitions. Where so coming to Lambert's law, tells that when a monochromatic radiation is passed through the solution, the decrease in the intensity of radiation with the thickness of the solution is directly proportional to the intensity of the incident light. Let I be the intensity of incident radiation and X be the thickness of the solution. So the next law is, that is Beer's law. We all know that the sentence of the Beer's law, that is when a monochromatic radiation is passed through a solution, the decrease in the intensity of radiation with thickness of the solution is directly proportional to the intensity of the incident light as well as the concentration of the solution. Let I be the intensity of incident radiation and X be the thickness of the solution and C be the concentration of the solution. So Beer-Lambert's law, that is A is equal to epsilon CL and T is equal to I bar I naught, or minus log T is equal to log I bar I naught is equal to A, that is absorbance. From the equation, it is seen that the absorbance, which is also called as optical density of a solution, is a container of a fixed path length, is directly proportional to the concentration of the solution. So principle of UV visible spectroscopy, that is the UV radiation region extends from 10 nanometer to 400 nanometer and the visible radiation region extends from 400 nanometer to 800 nanometer. Near UV region, that is 200 to 400 nanometer, and far UV region, that is below 200 nanometer. For UV spectroscopy is studied under vacuum condition. The common solvent used for the preparing sample to be analyzed is either alcohol or hexane. And these are the possible electronic transition can be graphically shown. That is, this is the energy, and these are the possible electronic transitions. The lower electronic level, that is sigma, and above that there is a pi and n, that is non-bonding, and pi star and sigma star in the above region, that is anti-bonding molecular orbitals, and pi and sigma are the bonding molecular orbitals. So the possible electronic transitions are sigma sigma star, sigma pi star, pi to pi star, n to pi star, and n to sigma star. So the different types of transitions I am going to tell in detail about those transitions. First, coming to sigma star transition. Sigma electron from orbital is excited to corresponding anti-bonding orbital sigma star. The energy required is large for this transition. For this transition, the energy required is large. So example, methane has CH bond only and can undergo sigma star transition and shows absorbance maximum at 125 nanometer. So coming to pi star transition, pi electron in a bonding orbital is excited to a corresponding anti-bonding orbital pi star. Compounds containing multiple bonds like alkanes, carbonyl, nitriles, aromatic compounds, etc. undergo pi star transition. Examples for this are alkenes generally absorb in the region 170 to 205 nanometer. Different type of transitions. The another type of transitions are n to sigma star transition. The saturated compounds containing atom with lone pair of electron like oxygen, nitrogen, sulfur, and halogens are capable of n sigma star transitions. These transition usually requires less energy than sigma star transitions. The number of organic functional group within n sigma star peaks is UV region is small, 150 to 250 nanometer. And so coming to n pi star transition, an electron from non-bonding orbital is promoted to antibonding pi star orbital. Compounds containing double bond involving heteroatoms C double bond O, C triple bond N double bond O undergo such transitions. N to pi star transitions require minimum energy and show absorption at longer wavelength around 300 nanometer. So in pi to sigma star transition and sigma to pi star transition, these are electronic transitions of forbidden transition and are only theoretically possible. Thus, n sigma star and pi to pi star electronic transitions show absorption in region about 200 nanometer, which is accessible to UV visible spectrophotometer. The UV spectrum is of only a few broad of absorption. So coming to next topic, that is charge transfer transition. Charge transfer is a very important process being responsible for the intensity UV or absorption of a large number of inorganic and organic species. In order to exhibit a charge transfer transitions, it is necessary that one of the component have electron donor characteristics and other have acceptor properties. So coming to ligand field transition, that is ligand possess sigma star, pi star and non-bonding molecular orbitals. If the ligand molecular orbitals are fully charged, the charge transfer occurs from ligand orbitals to empty or partially filled metal d orbitals. The absorption that arises from the process are called ligand to metal charge transfer bands. Forbidden transition may also take place, giving rise to weak absorptions. So these are my references. Thank you.